Okay. I say hello everyone once again. I started the recording, but even though we run this recording, don't hesitate to ask your questions over the lecture at any time. Just unmute your mic and ask your questions. Of course, you can also type your question in chat, but I might overlook that. Okay, so the title of the first lecture is Calculus and Complex Functions. So again, this course is graduate level, and all these concepts, these things, topics, including calculus, complex functions, vector operations, fields, is a part of your prerequisite. So you supposed to be already kind of aware of all these concepts that I plan to talk about. But since this is not my first year, right, I'm kind of aware about the need to remind students about all the concepts to be, I mean, to catch up. So calculus, complex functions, and let's see what it also will include in this first lecture. So this course is about numerical analysis of electrical devices, and in short, or like briefly, right, it's based on electromagnetism. So like concept, any aspects of interaction of electromagnetic field with matter, with devices, in order to achieve some functionality. And in electromagnetism, we deal with mathematical objects of different kinds. Let me write down this. In electromagnetism, we deal with, and so sorry for my handwriting, okay? We deal with math objects of different kinds. And also sorry about the barks of my dog. Different kinds. So what kind of mathematical objects we use? So first of all, scalars, right? The scalars. So for the scalars, what we usually have. So for example, pi, right? This pi number, which is 3.14, 15, etc. So this is the rational constant that you can meet in all formulas. Another scalar is electric charge. Like the charge of electron or hole. The mass is also a scalar. And of course the constants, like fundamental constants, for example, c, the speed of light. I mean, saying light, of course, we mean electromagnetic field or free space propagation of electromagnetic field. You know that electromagnetic field and light, basically two manifestations of the same thing, electromagnetic field. and the difference only the frequency. So the speed of light and also the other fundamental constants like epsilon naught, like electric constant, or permittivity of vacuum, and mu sub zero, which is magnetic constant. I heard some noise. Do you have any questions? I see Juan is unmuted. Let me mute him. Unless you have any questions. So scalars. Scalar is very simple. It doesn't change as we change the position coordinate. Scalar doesn't change. Another math object is a scalar function. Scalar function. Oh, we can denote them by like some f of x. X can be some sort of a variable. For example, coordinate, it can be temperature, can be pressure, something else. Of course, we deal with functions of several variables like x, y, z. In this case, they denote coordinates. We can also have some functions of t, of time. And an example of scalar function in electromagnetism is, for example, rho, which is charge density. Right. This is a function that we use to describe a continuous distribution of charge density. So the object number 3 is a vector function. Vector functions. Vector functions. So the vector functions, I mean, example in electromagnetism, vector functions could be electric fields, right? We denote vector by this small arrow on top. And for example, in terms of, I mean, in the case of electric fields, it can change upon the coordinates, and also it can change in time. So it can be a function like this. So this is electric. Um, the magnetic counterpart is magnetic field. This magnetic field. And other types of vector functions, I can bring the D field and the B field. These are auxiliary fields that we use to describe electromagnetic fields in matter. Of course, another example of vector function is radius vector. So radius vector indicates the position in space, right? So we use radius vector to indicate the place in space we refer to. Very important one. And of course, one vector functions can depend on other vector functions. And one example could be the electric current vector, which is the vector itself, but also depends on another vector function r, radius vector. And this basically means that the current in space is distributed somehow. It changes in space, and yeah, so to address that, to indicate that, we need to have this vector function depending on another vector. And another object, I guess the last one, is a more sophisticated object called tensor, and tensor functions. So if you never heard about tensors, you actually heard, because any vector is already a tensor. So vector is a tensor of first rank, but usually when we say a tensor, we mean the object of rank more than 2, and I mean including 2. For example, a tensor can be represented by a matrix with components, for example, epsilon ij, right? And gets matrix with components epsilon 1 1, epsilon 1 2, epsilon 1 3. So the first index refers to the rows, and the second denotes the columns. So this is the first element at first row, the first column. This one is the first row, second column, etc. So the second row is epsilon 2 1, epsilon 2 2, epsilon 2 3, epsilon 3 1, epsilon 3 2, epsilon 3 3. So this is a matrix, and not any matrix is a tensor, but any tensor can be represented in form of a matrix. And if this is a tensor, it must, I mean, its components must transform in a certain way to be a tensor. So usually these epsilon, these components are functions. Like some particular component ij would be a function of x, y, z, t, for example. And each component is a function. As like in the case of a vector, we have one column, right? Like e x, e y, e z. I could use 1 2 3. It doesn't really matter. And these ex, ey, ez, of course, are functions of coordinate and time. Coordinate and time. So, for example, ex is a function of x, y, z, and t, if the problem is transient. Okay, so this is about the objects. So in terms of physics, not any mathematical object can represent a physical quantity, physical reality. For example, one may ask why we use these vectors, tensors, scalars, why we cannot use some sort of arbitrary matrices, something else. So why tensors, why vectors, right? And that's because of the concept of covariance. So let me write this down. This note. Let me write this like a note. All physical quantities must be represented by covariance objects. So what does this word covariant mean? So let's recall this very fundamental equation. F equals ma, right? So Newton's second law, the main law of classical mechanics. F stands for force, m stands for mass, a stands for acceleration. And you see that we put this arrow on the left and on the right. So on the left and on the right, we have vectors. And for example, writing something like this, like vector on the left and scalar on the right, would be a mistake. Why? Because when you bring math, right, to describe physical systems, you need to choose the coordinate system, some particular coordinate system. So we live in three-dimensional space, and we can use this Cartesian coordinate system to describe a system, I mean electromagnetic system. So usually we denote this axis x, y, and z, right? And we also assign the unit vectors I, j, k, this. And then as we set the coordinate system, we can describe the things. For example, this force, right? So for example, we have some force distribution. This is the force. And I calculate the acceleration that this force causes. Of course, the force itself, it's a physical quantity, and it doesn't depend on the choice of the coordinate system. For example, I can now rotate this coordinate system anyhow, right? I can reflect it, I can rotate it. Of course, it doesn't change the vector itself, because this vector f is a physical thing. But this vector, as we set the coordinate system, this vector gets the components in this particular coordinate system, fx, fy, and fz. And of course, when you rotate this coordinate system, these components, they change. Fx change, fy change, fz change arbitrary, but this concept of covariance dictates that this object must, I mean, the components of this object, this force, must change in a way to keep something invariant. Something invariant. For example, in the case of the vector, we have the lengths of the vector. We denote it as a module, right? And I mean, from geometry, from basic elementary math, we know that the length of a vector is just the sum of the squares of its components. Y squared plus xz squared square root. So you can change the coordinate system. The components change, so they depend on the chosen coordinate system, but the length of the vector doesn't change. So this is invariant thing. This is the, I mean, why we use vectors. And if we go back to this Newton equation, second Newton law, if we set the coordinate system and then rotate it, the components of f will change. The components of acceleration will also change, but they have to change in a way to keep the length unchanged, invariant. So, and that wouldn't be so if you have, for example, vector on the left and scalar on the right. Then it would be I mean, that wouldn't work. So that's why vectors and tensors for the same reason. So when we change the coordinate system, the components of the tensor being functions of coordinates, they will also change. But they have to change in a way that keeps something invariant. In the case of such a 3x3 tensor, it would be, for example, a determinant of this matrix. Okay, so saying this, let me start the first topic today. Let's number it 1-1, and it's called calculus. Calculus. I mean, we're doing just recap of calculus, basically the things what you very well know. Calculus. So we have functions, we have vector functions, tensor functions, and when we solve a problem, do simulation, we interested basically in how fast this function change in space and time. Right. We need to write this down. So how fast the function changes in space. How fast? And there is a concept, there is a mathematical operation that answers this question, and it's called derivative. Right. Derivative. So what is derivative? Suppose I have a function f of x, and I calculate or evaluate this function in a particular point x, and then I jump to another close point in space by delta x, right? And of course, my function can also change. So I substitute for x plus delta x, and this delta x is the step of the change of the coordinate. And of course, in the result of this function will change, And in order to calculate the value of this change, um, the value of this change, I write delta f, which is also function of x. Right. And by definition, it will be fx plus delta x minus fx. So I basically take the final value of the function and subtract the initial one. But of course, this depends on delta x. The larger I take this delta x, the stronger this change. And in order to evaluate the ratio, I mean the thing that is not that doesn't depend on delta x, I simply normalize this change of delta f by delta x. So it will be fx minus plus delta x minus fx divided by delta x. Okay, and now what I should do, I just should make an assumption that delta x vanishes. So it's basically very, very small. And I do that. I mean, so now make delta x very small by this limit operation, delta x to 0. Right. So I write limit delta x to 0, delta f of x, delta x, and this is nothing but the definition of the derivative dfx over dx. So basically, when you turn this delta x to 0, your delta x becomes dx and delta phi becomes d phi. Right. So this is the definition of the derivative. And sometimes, I mean, it depends on the writing. We can write something like f dash x, or more specifically, if the function depends on a number of arguments, then we can indicate that this derivative is specifically by x. Right. So let me write this definition. Df over dx is equal to limit dx to 0, fx plus dx minus fx over dx, and that will be framed as this formula like this. So let's consider a very simple problem. Problem 1.1. So given a function of x to the power of 2, what is the derivative of this function? So I mean, don't without using the formulas, but using this definition of derivative. So basically, I write df over dx, right, and then my so df over dx, my f is x squared, so I have to make x plus delta x, so x plus delta x squared, right? Because my function is x squared. Then I have to subtract x squared, the function itself, and divide by delta x, and of course upon delta x going to 0. Right. So now I can express this x plus delta x squared to x squared plus 2x delta x plus delta x squared. Then this minus x squared left and divided by delta x upon delta x going to 0. Right, so it's equal to the x square cancel out, right? And then delta x can be cancelled in the numerator and denominator. So finally I get 2x plus delta x upon delta x going to 0. And now I conclude that if I make my delta x very, very small, it will be much smaller than 2x. So I can keep only 2x in the final result upon delta x, like vanishing delta x. Yeah. So this is the result. The derivative of our function x square derivative x equal to 2x. Pretty simple. So let me describe another problem 1.2, and basically the same, but another function f of x is equal to square root of x. Right, square root is the opposite mathematical operation to the polynomial function. Right. So what is the derivative of this function? So we do basically the same. Df over dx equal to dx going to 0, and then this square root of x plus delta x minus square root of x, the function itself, divided by delta x. So in this way, I cannot assume my delta x vanishing, right? Because it is in the denominator, and it will make this ratio infinitely large. But we can factorize this delta x in the numerator so it cancel down with the delta x in the numerator, and we will get the final result, the result that is finite upon delta x vanishing. So, well, to do so, I can use this trick. I can multiply and divide this ratio by the same thing. So this is my numerator. So my numerator delta x. So I multiply numerator denominator by the same thing, x plus delta x, and then plus square root of x, and divide it by the same thing. Why so? Because now I can use this formula a minus b times a plus b, right, which is a squared minus b squared. And of course this delta x here vanishes. So it's equal to, in the numerator it becomes x, then plus delta x minus x, and then divided by delta x, x plus delta x plus square root of x. Very good. And now this x again cancel out, and we've got this delta x, which also go away, and I have finally 1 over square root of x plus delta x plus square root of x, and delta x going to 0. So now I can assume this delta x going to 0, because if it is, I mean, if I substitute 0 for delta x, it's not a terrible problem. No terrible problem here. It will be just equal to 1 over 2 square root of x. So this is the answer for this problem. So the derivative of square root of x is 1 over 2 square root of x. And of course, the same way you can obtain, or I mean, or similar way, or other using other approaches, you can obtain basically any formula for the derivative. And let me, for as a reminder, let me write down several formulas that will be of that we will use in our course. So for formulas for derivative derivatives. So the derivative of a constant, of course, 0, because the constant doesn't change. It's not it doesn't change. That's why it's 0. Basically, f of x plus delta x and f of x equal to each other, so it gives 0. Next, generalizing these two problems that we just solved, we can write that derivative of x to the power of n, derivative of x by x, is equal to n times x to the power of n minus 1. Right, so you just bring the power in front of the x, and then the power is equal to n minus 1. So another important one is the derivative of sine x by x is equal to cosine x. Same way, cosine, derivative of cosine x by x is equal to minus sine x. Another formula is for well, the logarithm by, I mean, with base e is equal to 1 over x, right? And for arbitrary logarithm log with base a by x, it will be again 1 over x, and then also divided by logarithm a. Yeah. So if a is e, 2.7, etc., right, it becomes 1 for this logarithm. What else? I mean, of course, exponential function e to the power of x, derivative by x, gives you just e to the power of x, which is very nice for, I mean, particularly for electrical engineering, because as we will see soon, many quantities, quite often, the things can be represented as an exponential function, and then all the differential equations that contain these derivatives, they get simplified very strongly. So the things that the use of these exponential functions make the life much simpler. But what happens if we use another base, like a to the power of x? So the result is basically similar. It's still this exponential function a to the power of x, but also multiplied by the logarithm of base e of A. Right. Yeah. So these are the formulas for taking the derivatives, and we also need two rules. Change the color. So the first rule is a product rule. Product rule. So product rule says that it's, so say we have two functions fx, gx, and we take the derivative by x. So what we do, we take the derivative of the first one times the second one plus the first one times the derivative of the second one. So this is so-called product rule. Pretty simple. And the second rule we need is the chain rule. So chain rule says that so if we have a function that depends on another function of x, something like this, right? So, one example could be something like sine, which is already a function, but it can be a function of, let's say, x squared. X squared is another function, so it's a function of x. So when we have this situation, function of x, and we take the derivative of it, we have to first take the derivative of function f by this function g, and then multiply this by derivative of the function g by x. Right, so that's why it is chain rule. So for example, applying this for the taking the derivative by x, what we get? The derivative of sine by its argument is cosine, so write cosine x squared, and then we have to multiply this by the derivative of the function x squared by x, which is 2x. This is the this is the application of the chain rule. So far we consider it only a function of one argument, but of course a function can be a function of several arguments, for example 2, like xy, right? And that means that um, taking derivative, we can take derivative by x of this function, and we denote it by this curly df xy dx. So this is for the partial derivative of the function of several arguments by one of it. And by definition, it is v dx to 0 f x plus delta x, and I keep y here because the function is of several arguments, f x y, then divided by delta x. But this is just one option. Of course, I can take the derivative by another argument, and it will be dfxy over dy. And this is nothing but dy going to 0, fx y plus dy minus fxy over dy. Right, pretty straightforward. So now Um, so I have a function of multiple arguments. And I change x, I change y, and I see my function changing. But what if I change this function arbitrarily? It's like I change both x and y, or even, I mean, for a more general case of a function of 3 arguments. What if I change all of them like simultaneously? In that case, I bring this concept of differential. Differential, right? And let me consider a function of 3 arguments, x, y, z. So in this case, when I change the arguments, I can calculate the derivative by x, derivative by y, and derivative by z. So what is the the total change? Total change in the arbitrary direction. And let's highlight this word arbitrary. So arbitrary direction. So in this case, when x changes, y changes, and z changes, I write the change for the function as a differential of the function. So it will be d, because the change is very small. So it's df x, y, z. And the change itself is written as this construction df over dx. So first I change this x, right? And multiplied by dx. Then I plus df dy, dy, and then plus df dz, dz. So all these dx, dy, dz, they are just small changes of the corresponding argument. And when I change that, my function gets changed by this amount, df over dx. So I change x, it changes by df over dx. I change y, it changes by this amount. I change z by this amount. And the total change is just the sum of 3. And let me maybe highlight this formula because it is important. So this is pretty important. Let's name this differential. Differential. So guess let's consider a problem 1.3 for the function f x y, which is x times, for example, e to the power of y squared. Find the differential of this, total differential of this function. So for the total differential of this function, by definition, is equal to df over dx, dx plus df over dy, dy, because no z here. Right. So what is df over dx, partial derivative? Here we have x times a function of y. So when I take the derivative by x, I assume y constant, so it doesn't change. It's like a constant. So I take it from the derivative, and it's equal to e to the power of y squared. And derivative of x by x is 1. So this is the answer for this part. Then df over dy. Again, when I take the derivative of y, I keep x unchanged, so I can take it out. And then partial derivative of e to the power of y squared. I apply chain rule, so it's equal to e to the power of y squared. And then I also have to multiply by the derivative of y squared, which is 2y. So the answer is df equals to e to the power of y squared dx plus 2xy e to the power of y squared dy. This is the answer for this problem. Again, this is the total derivative or differential of a function, which describes how fast the function changes upon simultaneous change in x and y. X and y. What was that?
I have one question. Can you hear me?
Yes, but please speak a little bit louder.
Okay. In the last line, we have dx and dy. What does that indicate actually? Like
This is
in the last
this,
line.
yes.
Yeah, that
So,
one.
yes, this dx dy, they came from this formula dx dy. So it indicates the small change in x. Small change in x. So let me go up to that point where we discussed that. Here. Yes. Here. So basically, delta x, when it goes to 0, it turns to dx. And the same for dy and dz. When you assume it very small, then you substitute delta x by dx.
Okay. But we have the differential derivative d of f over
Yes.
delta x. The one in the denominator is also the change in x, right? But
No.
if we look the line on the before the last,
Yes. So this
yeah.
is for differential. Let me repeat this point once again. So this is not derivative, this is differential. This is the function of several arguments, x and y. And in order to turn this to derivative, for example, by x, now I would need to divide this line by delta x, right? So it will be df over dx, and I will get e to the power of y squared, and then dx over dx, which gives me 1. But then plus 2xy e to the power of y squared dy over dx. But when y changes, x doesn't change. And when x changes, y doesn't change. So this term is 0. This term is 0. And that makes the partial derivative, which actually has to be written in this way, df over dx. So this sign here denotes the partial derivative. It's not total, that's partial derivative. I take the derivative by x and assume that y doesn't change. So it's equal to e to the power of y squared, as it's supposed to be. But this is just a part of change of the function, because in general case, both x and y, and if we have z and other arguments, they also change simultaneously. In order to keep in track all these changes upon x, upon y, we have to write the we have to write the change of the function in the form of differential. See? So from the formula for differential, you can get partial derivative, but partial derivative doesn't describe the entire change. So that's why basically we need this formula for the derivative, and that's why I frame this derivative formula in red frame. So if it's not clear for now, then probably you should think about this more. And also you'll get the home assignment, so you will get a chance to practice this.
Yeah, now I can differentiate between the partial derivative and the derivative, the whole thing. Yeah, thank you very much.
Awesome. Yeah, feel at any point, feel free to ask questions. So, so if I have a function, right, I can take the derivative or partial derivative, and after that, I also get a function, which also can be differentiated more. So let's write this down. After differentiations, we get another function that can be further differentiated. And that brings the concept of second order and third order differentiation. Right. For example, if I have a function f of x, y, then the first order differentiation could be fx, right, which is df over dx, or fy, which is df over dy. But after that, I mean, of course, this df over dx is another function, and it can be also differentiated. So, for example, for the second order, we would get something like f double dash xx. So xx means first differentiation on x, second is also on x, and it's equal to d2f over dx squared. So this way we denote the differentiation of a function x and x again, basically by x twice. We would get also double dash x, x, y, and it would be d2f dx dy. And finally, f double dash y, which is d2f dy squared. Okay. So in order, I mean, in terms of this mixed differentiation, when we differentiate the function by x and by y, does the order of this differentiation make any, I mean, is the order important or not? So it's not that obvious, but the answer is that the order is no matter. So you can basically make this differentiation by x and then by y, or by y then by x, and the result will be the same, provided that the function is provided that the function has differential. And this is something that bears the name of Clairaut, right? Clairaut. Let's Clairaut theorem. Something like this. I might be wrong, but Clairaut theorem. You can write this like this: d2fxy over dx dy is equal to d2fxy dy dx. This is also pretty good result. So far it was about scalar function f, x, y, but what happens when we, like, how to take the derivative of a vector function and tensor function? So differentiation of vectors and tensors is basically conducted via components. Differentiation of vectors and tensors is by components. What it means? It means that, for example, if I have a vector A, and the vector itself is a function of x and y, for example, for x and y, and I can represent this vector by the column ax, ay, az in the xyz coordinate system. In another coordinate system of another type, like spherical coordinate system, it would be ar, a theta, a phi. In cylindrical coordinate system, it could be a rho, a z, a phi, something like that. And of course, these components, they are functions of xy, xy, xy. So all components of vectors, of vector that is a function of x and y, the components also functions of x and y. Right. And when we take the derivative of components, for example, ax by ax, we can also take the derivative of ax by y, right? And the total derivative of the of this particular component ax is also will be ax dx, the dx plus dax, the same component, by dy, right? So x here stands for vector component, And the vector component itself is a function of coordinate x and y. And for the total differential of this component, we have to take both terms for the x and y. If this component of the vector would be a function of z, it would get another term plus dAx dz dz. And but this is just for the first component. For the second component, we get the same day dx dx plus day dy dy. And finally, for the last component z dA z dx dx plus dA z dy dy. Right? And of course, the vector itself is a function. So I could, instead of doing the differentiation by components, I can write something like this: dA vector function x and y, dA vector over dx dx plus dA vector dy dy, something like this. And these two, of course, the same. So if you represent this dA vector by components, you will get these three formulas. What I forgot to mention, yeah, and of course for the tensor, right? Epsilon I j. It also can be a function of several arguments, and for the components of the tensor, I can also write the differential. Let's take it around 3, for example, in this case. So it will be d epsilon eg dx dx plus d epsilon eg dy dy and plus d epsilon eg dz dz. Something like this. So these different differentials of tensor components will show how this tensor depends or changes in space upon changing x, y, and z. Do you have any questions by this moment? Very good. Then let's discuss integration. Integration. Again, just a reminder. So basically, integration, I mean, physically speaking, integration is opposite to differentiation. So integration opposite to differentiation. Differentiation shows how fast a function changes from point to point, right? In contrast, integration integral, what it does, it accumulates the change over certain interval. I'm not sure should we write this or not. So basically, we can, yeah, so what's important here is this fundamental theorem of calculus, right? Fundamental fundamental theorem of calculus. The fundamental theorem of calculus. So basically, if a function f of x is an antiderivative, anti of f small x on interval of AB, then the integral denoted by this curved line from a b of function fx dx is equal to the difference of antiderivative. So basically, antiderivative in the point in the final point b minus antiderivative in the point a. And this is something that bears the name, and it's this name of fundamental theorem of calculus. Uh, so basically, it says that the integral is a opposite operation to differentiation. Right. So let's maybe consider this a little further. So let's suppose that we have function f small, and we can take the derivative of this function, and the result of this derivative is another function. And let's name this function g. So if this gx is equal to df over dx, f is a function of x. So formally, I can multiply both sides by dx, and I will get gx dx on this side, right, is equal to df. Gx dx is equal to df. So formally, it's allowed to manipulate these differentials. So it really works like a ratio. You can multiply this ratio by dx. So you will get gx dx on the left and df on the right. And now I do this operation of integration, right? So I say that I integrate both sides. So I will get something like this integral here, integral here, gx dx equal to df. Okay. This is basically how it was, how you deal with the integral. And now, since this differentiation, since integral is the opposite operation to differentiation, so this part becomes f, because integral of differential gives you the function itself plus some constant, because if you take the differential, if you take the differential of this function f plus constant, the constant will go on because the differential of constant is 0. Right. Yeah, so basically the result is this g of x dx gives you f. plus some integration constant c. So basically that's why, or in this sense, the integral is considered to be the opposite operation to the differentiation. So numerically, this integration operation is nothing but taking the sum, right? Taking the sum of small but finite delta f. Small but finite delta f. Let's say if you need to take an integral of some function f, which can be a component of a field, right? Then, for example, in MATLAB, you have to use this summation operand and take the finite change in the field, in the function, and if you want to connect this to the change in the coordinate in space, you can write something like this. You can divide it by delta x and multiply it by delta x. Yeah. And for the future, we will again need some formulas. For the integral. The first one, of course, the integral of some constant a dx. So the constant can be taken out from the integral, and then the integral of dx gives you just x plus the integration constant. So it's equal to ax plus constant c. So c constant, integration constant. Another formula is for the polynomial function x to the power of n dx. So in this case, we divide by n plus 1. For the derivative, we had n minus 1 and multiplied. So in this case, it's divided by n plus 1, and the power is increased by 1. So x to the power of n plus 1. Let's take the derivative of this and check that this is really the opposite operation. So 1 over n plus 1 x n plus 1, and I take derivative by x. So I take n plus 1 out because it's constant, right? And then derivative of x to the power of n plus 1 by x gives me n plus 1 here, and the power of x by 1 less. So it will be x to the power of n. These two cancel out, and I get x to the power of n. That's what I expect to get for the, since this x to the power of n was the integral function. All right, so this is the second formula. The formula we also will need for the sine and cosine. So for the, let's start with sine. So for the sine x dx, we have minus cosine x. Again, why? Because the derivative of cosine gives me minus sine, and this minus must be cancelled by this one that we put here to get sine under integration integration operation. Minus cosine. So for the cosine function, get just sine x, because differentiation of sine gives me cosine, so it's correct here. For the integral of the exponential function e to the power of x dx, one of the most important formula is still ex. So integration, differentiation doesn't change the exponential function. And of course, I mean, plus c plus c plus c everywhere, plus this integration constant for the unknown integration intervals. We have to add this integration constant. So this is for the integral of e to the power of x, and another one integral from a to the power of x. A is arbitrary, dx. So apparently we get a to the power of x, but then divided by natural logarithm of a. And here I must say that so first of all, not the logarithm is defined for the a larger than 0, right? And also, since this is the ratio, the logarithm of a cannot be equal to 0, which happens when a equals to 1. So this a must be positive and not equal to 1. Yeah, so basically this is about differentiation and integration. We already have 7. All right. So the next topic is vector operations. Simple vector operations. 1.2 vector operations. Vector operations. So suppose I have two vectors, A and B. Two vectors A and B. So using these two vectors, what kind of operations I can do? I mean, of course, I can sum them. I can multiply them by constant. That's trivial. More important operation is the dot product. Dot product, which is by definition gives me constant c, and I denote it by a dot b. That's like dot product, or it's also that's named inner product, and scalar product. Scalar. So in different textbooks you can meet different names for this operation. So usually it's by this dot between two vectors, and it gives me a constant. So the geometrical meaning of this operation is that I take one of these vectors, for example, vector b, bring the second one, vector a, its beginning to the beginning of the vector b. So basically I bring this vector a to the vector b, and take the normal of vector a to the direction of vector b, like this. So in result I will get this angle phi here between these two vectors, and from this geometrical meaning I see that if the vectors a and b are orthogonal, or normal, right? So the projection of the vector A on the vector B will be 0. So it must be described by cosine of this function, because when phi is equal to 90 degree or pi over 2 radian, the result must be 0. So the result for this operation would be the length of the vector A, the length of the vector B, and multiply by cosine this vector or this angle phi. And when vector A is orthogonal to vector B, which means right angle between them, then A dot B will be equal to 0. And when they are collinear, right, then this C, the result will be just the product of the length of vector A and vector B. So what's important also to 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 remind here is that, for example, for our coordinate system x, y, and z with unit vectors e, g, j, k, right? These I, j, k unit vectors, they also vectors, and so what's the dot or inner product of them? So for example, if I take I and then make the dot product with j, of course the result will be 0 because these two vectors are orthogonal, as well as the product I and k and k and j, so always the result will be 0. And of course the I times I vector, which is I squared, is equal to 1, because the projection of a vector on itself is equal to the length of the vector. And in this case, the length of these unit vectors is 1. Is 1. So this is the dot product or inner product. There is another operation named cross product. Cross product. And cross product provides me another vector from these two. So I take A cross B, and it gives me another vector, which is normal to both, to vector A and vector B. How we calculate this product? Suppose we have a vector A with components AX, AY, AZ, and vector B with components BX, BY, Z, right? So the result of the cross product is determinant. Let me denote determinant by two vertical lines. So it will be determinant I with components I, J, K, AX, AY, AZ, the first vector, BX, BY, BZ, the second vector. So these two vertical lines denote determinants. So this is so let me remind you what the determinant is, right? For some arbitrary matrix, let's say we have matrix 2 by 2 first, with component C11, C12, C21, C22. Determinant. So determinant, again, this is not matrix, right? This is determinant of the matrix. I will denote matrix by one vertical line. So determinant of the matrix. So in this case of the matrix 2 by 2 is very simple. It's just product of these two diagonal elements minus the product of diagonal elements. So it will be C11 times C22 minus C12 times C21 by definition. This is determinant. And as we discussed in the beginning, if this matrix corresponds to a tensor, then this determinant is nothing but the invariant of the tensor, invariant of this matrix. It means that if this matrix didn't describe some physical quantity, and when I rotate the coordinate system, the components of this matrix being functions of coordinates, they change, but the determinant is invariant, it doesn't change upon this coordinate system rotations. And this is very, this is basically what allows us to build any theory, including electromagnetism. But this matrix, this determinant here, it gets the matrix 3 by 3, right? So we need to generalize this to the matrix with 9 components. So for the determinant with component C11, C12, C13, C21, C22, C23, C31, C32, C33, determinant. We use this approach of minors. Approach of minors. How it works? Again, just remind you. So first we take one, the first element, and then we cross out the corresponding column and row from this matrix, and we get this submatrix, which is called minor. This is minor in this case. Then we sum up the indices of this element. In this case, it is 1 and 1, which gives us 2. And 2 is even number. So for even number, we put plus. Then this element itself, C11. And then by determinant of this submatrix, C22, C23, C32, C33, submatrix. Then second element here, I cross out the column and the row. The indices 1 and 2, the sum of them is 3. 3 is odd, so it makes me to put minus here. Then the element C12, and then the determinant of the submatrix, which is left after this crossing out the row and column. So it will be C21, C23, C31, C33. Okay, and then apparently plus, because 1 plus 3 is 4, C13, and determinant of C21, C22, C31, C32. Okay, and then we've got these 3 determinants which are 2 by 2. We can use this formula above to expand them and get the final formula. So this way, after you do this calculation, you can get this formula for the cross product for this cross product above. So it will be C vector is equal to I unit vector along x direction a y b z sorry, z minus a z b y, then plus j a z b x minus a x b z, plus k a x b y minus a y b x. So all these are, so first of all, this is vector. And this vector gets several components. This is the first component of this vector, cx. This is cy, and this is cz. Right. So it might look bulky, but it's very easy to remember it. Actually, for example, for the first term here, I a y b z minus a z b y. How I remember this, I mean the order is right. So this I it corresponds to x. It's a unit vector along x direction. Then it gets this y here, z here, right? And then the second term is just flipped components, zy. So and basically, if you go the cycle x, y, z, from x to y, from y to z, and from z to x. So you basically get all these components in this formula. All these components in this formula. What else for today? Yeah, so this is the cross product. We also have another type of product, which is triple product. Triple product. It's very simple. It's just the mixture of two. A dot B cross C. So we have the both, basically, the cross product and the dot product together, and without discussing that much about this, it's just a determinant of the components of the three, ax, ay, and z, bx, by, bz, and cx, cy, cz. Yeah, and if you expand this determinant the way we just did, you will get the formula for this one. And geometrically, it is the volume of parallelogram based on these vectors. So it's basically like if you have this vector b here, then some vector c here, the cross product generates the vector orthogonal to b and c. And if you have another vector here, a, right, a vector. So this triple product, it's basically equal to the volume of this parallelogram that is built from these three vectors. So like this is the volume. It's equal to this determinant here. This is the product number 3, product number 4. is so-called tensor product. Tensor product. So tensor products, first of all, very important, right? When you discuss any things like, for example, I'm teaching this semester quantum computing, and we need tensor product quite a lot in that area. Also, artificial intelligence, any sort of computing, imaging, processing, etc. Everything. Tensor product is everywhere, so it's very important to understand what it means. So by the name, tensor product generates a tensor from two vectors. Let's denote it by Cij, like tensor of second order. And it's a result of tensor product of two vectors, A and B. Right, so this circle with cross inside, it denotes the tensor product. How we calculate this tensor product? Suppose we have this vector A with two components, AX and AY, for simplicity, and another vector B with components BX and BY. And then tensor product is nothing but the product of each component of the first vector by the second vector. So it will be another vector with components AX multiplied by vector B. And the same for the second component AY, BX, BY. And now if I expand this, simply multiplying by component X by the components of vector B, I'll get something like this: AX, BX, AX, BY, AY, BX, and AY, BY. It's another vector of four components. Pretty simple, huh? And finally, the final type of product is the number 5, so-called dyadic product. Dyadic product of two vectors. Dyadic product. So dyadic product is the same as tensor product with one simple difference here. So it's again product of vector A. The sign is the same, but the second vector I take the transposed vector. So basically, if vector B is the column of Bx and By, right, the transposed vector is the row Bx, By. The transposition means rotation of the vector or the matrix around its diagonal. So the vector becomes the column becomes this the row, and row becomes the column. And yeah, so in this case, it works exactly like previous. I have AX, AY, and then there's a product by the row BX, BY. And the calculation goes the same way. I have the first component here and multiply by the second vector, which is the row. Y, Bx, By. And when I expand the these things, I get what I've got: AX, Bx, right, from the first multiplication, then AX, By, then AY, Bx, and finally AY, By. So from two vectors, I've got the matrix 2 by 2. And if I would get two vectors of 3 components, I would get a matrix of 3 by 3 with multiplication of all the components of the corresponding vectors. So this is, and there is a theorem that says that this dyadic product gives you a tensor as a result. So this is the, of course, this is the tensor. Yeah, so I guess we can stop at this moment. Unfortunately, I was not able to discuss this complex function. We will proceed next next week. So let me stop the recording and then we can discuss the things.